So we have a conference about the demystification of the architecture-oriented event with Apache Kafka. I made an inline translation. And so this is going to be presented by Bogdan Sukashiu.
Cool.
The ground is floor. The floor is yours.
Thank you very much. And yeah, hello everyone, and thank you for joining the session. Unfortunately, it's going to be only like 20 minutes long, so if there are any questions, maybe we can spend some time afterwards in the hallway, and I'll try to answer your questions, if there are any.
You have only 20 minutes because we have someone after.
Yes, I know.
Maybe you can take some questions during.
Sure, that's also fine. I'm going to stick around for another hour or so, yeah, we'll have plenty of time to answer questions. Yeah, so my name is Bogdan Sukashiu. I'm a staff engineer at a company called 8x8, and I'm also a Pluralsight author where I create various courses, but mainly around event-driven architectures and mostly focused around Apache Kafka. So today's session is about event-driven architectures because there is a myth that event-driven architectures are all about real-time systems, like being real-time, processing data in real time. However, this is just like a small part of event-driven architectures. They are building ETL pipelines, real-time ETL pipelines. Those are just a small part of event-driven architectures. In fact, event-driven architectures can solve a lot of other problems, and probably you won't even think about that. And yeah, theory is good, but we also need some practice, and I chose Apache Kafka because Kafka is one of the most popular way to implement an event-driven architecture. And yeah, let's start with the beginning. So as you all know, everything starts with a monolith. We have monolith architectures starting from, 20, 30 years ago, and they are really simple, right? We have a lot of code, which everything is condensed up into a single application, a single running process, and usually there's a database attached to it, so which can grow pretty large. There are some databases with, 100, 200, 300 tables. And yeah, it's simple, but it's also really powerful because you don't have to worry about ops, you don't have to worry about deployments and everything. Everything is just one application, so works really well. However, there is a problem, right? Because architectures, they all have trade-offs. And the problem with monoliths are scalability. If we condense everything, all the issues around monoliths, everything condensed into scalability. And there are two aspects of this. So the first one is the application perspective. If we need to process more requests, then we need to increase the number of instances. So if there are thousands and thousands more requests, we need more instances of the applications, and it's not really efficient because monoliths, we don't really need to scale the whole monolith, but just a part of it. And yeah, to solve that, some very intelligent people came with the idea, well, why not just split that and maybe also the databases and have that and have a service-oriented architecture. So take the monolith, split it into multiple pieces, and then we have the service-oriented architecture. The problem with service-oriented architecture is that the boundaries are not really well defined. There are soft boundaries, and some services can be larger than the others, and then you also can have those issues of scalabilities. But then microservices appeared, and microservices are all about domain-driven, being domain-driven. And each microservice usually is split around a domain. So we have the domain, the big business domain, which has multiple subdomains. Then we have bounded context, aggregates, and a lot of that stuff, which is which you can all learn about in domain-driven design. Yeah, also each microservice has ownership over the data, over some part of the data. So if we talk about an e-commerce application, we have users, we have orders, we have carts, and we have products and so on. And then we can have a domain for each microservice with the data attached to it. Also, another cool thing about microservices is that we don't really need to have the same database for each microservice. We can have NoSQL databases, graph databases, key value stores, any kind of database we want which matches our use case. So yeah, with microservices, we've actually solved the scalability problem, the issue we had with monoliths, and service-oriented architectures are now solved by microservices. However, in software engineering, there is not really good or bad, right or wrong. We have trade-offs, and the trade-off for microservice is data access. Because right now, data is really hard to access. We don't really have the data in a single place that we can just query it and get the full data spectrum that we need. Data is now encapsulated in each microservice. And yeah, if one customer wants to make a request, then that request just spans across tens or hundreds of other microservices depending on the business. Which gets us into some other types of issues. We have now dependency management issues, distributed transactions. We have to deal with coupling, with timeouts, and yeah, even data ownership, because each microservice needs to own just part of the data, and that's all. Yeah, so this is where event-driven architectures came into place. And I went to Wikipedia, I searched what event-driven architectures are, and I found this. Event-driven architectures are a software architecture paradigm promoting production, consumption, and reaction of events. So right now, we don't really have that database as the center of our architectures. We now have events as the center of our architecture. So how does it look like? If we take that full diagram and then we just simplify it, let's say we have a service that uses REST to communicate with two other services, and then a queue to communicate with another. We can actually transpose it like into a unidirectional flow of data. Now, to make this event-driven, we need to add another concept, and that concept is called an event stream. An event stream is just like a middleware between our applications, because right now applications are separated into two types. We have producers, and then we have consumers. Producers, they are responsible to generate the data, to generate the events, and then send them to the event stream. And then consumers, on the other hand, they are responsible to actually get the data from the event stream. There are also, we can also have the combination of those two. We have a producer. An application can be a producer and a consumer, and in that case, it's going to be called a streaming application. But what exactly is an event stream? Well, an event stream can be many things, or many protocols, tools. As long as you have a protocol that you can asynchronously subscribe to, then that can be an event stream. So we can have queues, WebSockets, reactive APIs, topics, logs, a lot of protocols, a lot of tools that we can use to get an event stream going. However, there is a slight difference between these types of event streams. For example, queues, WebSockets, and reactive APIs, they support only reactive events, whereas topics and logs, they actually use persistent events. So the main difference is that with reactive events, we can only consume the events once, and then they're gone. We cannot really get them back. With persistent events, with topics and logs, we can actually query them back. We can query them as long as we want, how many times we actually want them. All right, and yeah, if we transpose this model to Apache Kafka, this is how it looks like. So we have at the application level, we have a broker, a Kafka broker, which contains topics. So each topic is the event stream, can be considered an event stream. Or synchronous APIs, we have the idea of pushing the data. So the application that is contacted. So for example, we have a request from our consumer, and the backend application has to push data to some other services. In event-driven architectures, we actually have the opposite. So the consumer is responsible of getting the data from the event stream. Then we have the fan-out behavior. Multiple consumers can actually consume from the same event stream. So right now, data is really easy to access, right? Our data is in the event stream. The consumer just has to plug it in and then just get it there from there. Then we have the one producer type per event stream observation. So a topic can or it cannot be an event stream. And that depends on the type of data we have on that topic. So if we produce only one type of data on that event stream, then we're going to get, then it's going to be considered an event stream. If we produce more types, then just orders. If we produce only just orders on a topic, then it can be considered an event stream. Otherwise, if we produce more than one type, it's not going to be an event stream because we don't have that governance on that topic. The fourth and the last observations is that producers don't really know consumers. So from an architecture perspective, they are pretty well known, but from an individual application perspective, those are not really known. So the only job of the producer is just to produce data to that event stream, and that's it. It doesn't know who is going to consume it, if there are any consumers. On the other hand, consumers, again, they don't really know who they are getting data from an application perspective. They just know that they have to connect to that event stream and get the data from there. So yeah, with event-driven architectures, we've actually solved the data access issue. But as I said earlier, in software engineering, we have trade-offs. We don't have really good or bad. So the trade-off for event-driven architectures is consistency. We no longer have that strong consistency that synchronous APIs, especially REST, gives us, but now we have something called eventual consistency. And the key to building successful event-driven architectures is understanding and accepting eventual consistency, because I've seen a lot of people trying to manipulate and to transform synchronous APIs into an event-driven, even though they are not meant to be event-driven. So as long as you're accepting eventual consistency, you're good to go. So yeah, I've talked a lot about event-driven architectures, but what exactly is an event? In essence, event is just data, just like a message, because we want to transfer some data from one service, a service A, to a service B. And the summary, if we condense that, is just a message. A message is just data transferred from A to B, but that data must have a structure. And every message has different flavors, and depending on when the action is happening. So the first flavor is the command, right? If we give a command to another service, if we send a message to another service, that action is going to happen, is going to trigger some processing, in the future. And also in the command case, we may or we may not get back in a response. Then we have the queries, which always happen in the present. So just like interrogating a database, we want to get some data from the database. We launch a query, and then we get the actual data. That's why it's happening in the present. And then we have events. Events are actions that have happened or have been triggered sometime in the past. And also events are undirected. So we send an event to the event stream, and then we don't really know who is going to consume it. Based on that, we have two types of events. And the first one is event notification. Just like I said earlier, an event notification is an action that has happened in the past. And then the best example that I can give you is the suggestion carousel for e-commerce applications. So if you go to an e-commerce application, usually you have a carousel at the bottom of the page. And how is that carousel compiled? How are those suggestions actually compiled? Well, when you scroll down the page, you tend to focus on some various items, right? And what usually happens is you actually hover over that specific item. So for example, you want some new shoes or some jacket or some glasses or whatever, and you actually hover over that specific item. And when you hover over that item, an event is actually generated and sent to the backend systems. And when you reach the bottom of the page, you get the the suggestions. And yeah, it's really cool. Event notification are really cool because it really maps out that no response behavior. So you get the, you send data, but you'll never get back. This is just some code, some examples for writing a Kafka producer and a consumer. There are tons of examples like this on the internet. It basically takes like 10 lines to write a Kafka producer and another 10 lines to write a consumer. This is all in Java. So basically there are 4 blocks. So you have the configuration block where you specify where you can find the producer, where you can find the broker, and what kind of data are you sending? Are you going to be sending strings, JSONs, or binary serialization formats like AVR or Thrift or Protobuf? Then you have the creating the producer and consumer and the actual exchange of the data. I'm not sure if we can see anything in there. I hope so. So yeah, on the left side I have a producer running, and on the right side I have not 1 but actually 3 consumers. So I've just started the producer, and yeah, it's sending messages to the broker. And now I'm going to start the consumers. So the consumer 1, 2, and 3. So messages are composed of 3 things. So we have a key, which is an incrementing number right now. And then we have the value, which is a UID. And we also have headers, but I haven't really logged them in here. And yeah, it's really cool because with just like 20, 30 lines of code, I actually managed to get this done. Just try to think about how many lines of code, how much code it would take to do all of this, but in a synchronous manner using REST APIs. Cool. The next type of events are event-carried state transfer. So with event notification, it's all about that action. With event-carried state transfer, it's all about a change in the state. So and I took the address change event, right? A user that is connected to an e-commerce platform has that address persisted in there and just changes it. So the main question is, what should we put in that event, right? Should we put only the old address, the old and the new address? What about some user information? Let's say if we only go for the new address, we put that into the topic, into the event stream. Topics are persisted, so it persists the event, and then they are forwarded to the consumers, which are actually 3 of them. However, we find out that one of the consumers is actually a tax service, and tax services usually need needs the old addresses as well. So what's happening? The tax service will try to query back the producer, and this is actually an anti-pattern. So you shouldn't do this because event-driven architectures are all about decoupling, but now we're actually introducing coupling again. So try to avoid querying back the source system when you're using events. And another key point to remember is that events should still make sense in the data lake after 10 years. Just to keep in mind when you're designing your events to go for this approach. Cool. And the last section, I'm gonna try to go really fast through it. Yeah, thank you. Is the distributed source of truth. So right now our data is not in a single place. We don't really have a source of truth for our data, but it's distributed across an entire system of microservices. So what we usually tend to do is to actually copy data from one database to the other, but that imposes a lot of effort, like writing database synchronizers and making sure that our data is always up to date in the copied database. So this is where event sourcing can help us. Event sourcing is actually around us for a long time. 100 to 100 years ago, banks didn't have digital systems, so they had a transaction log. So they had to write up every transaction, and at the end of the day, they had to make the summary. So that's exactly how event sourcing actually works. So yeah, we have, let's say we open a bank account. The initial amount is 0, then we had 500 euros, then we add another 200, and finally we subtract the 300. To compile the current amount, the end of the day amount, or just the current amount, we just have to go through that log and perform all those transactions, right? So first we add 500, then we add another 200, so we have a total of 700, and then we subtract the 300, and then we get a current amount of 400. So that's all about event sourcing, just replaying events from the log. And actually Git is the most well-known event sourcing system, because Git doesn't store copies of the code base. They only store the differences, the transactions that are happening in the repository. And yeah, event sourcing, how does it work? So let's say we have the example from the previous example. We have 3 consumers, which are all consuming from the same event stream. Those consumers are actually going to retrieve those events from the event stream and then build up the state in their database. This technique is called materialized view. Then another event comes into the event stream, and all those consumers are actually going to receive it. The key thing to notice in here is that they are not receiving the events at the same time, but only when they are able to process it. So that's why we have to accept that eventual consistency, because events are not received all at the same time. Then let's say that something goes wrong with service with C2. Our database, has some faulty issues, and that's fine, because the others can actually still consume from the event stream, and everything goes well. Then the C2, the consumer 2, gets back its database online, but we had to discard all our data. This is also fine, because we can actually play everything from the beginning. And that was it. Thank you.
Thank you. Do we take one question? Okay. One question.
Cool.
Hello.
Hey.
I have a question about using Kafka. In my company, we use DDS. I don't know if you know what it is. Data Distribution Service from OpenSplice.
Okay.
And I wanted to ask King, but if you don't know, what was the pro and con to use Kafka versus DDS? But if you don't know,
I'm not really familiar with that service. If you can just describe it in like.
It's practically exactly the same as with Kafka.
Okay.
We use topic, and it's a middleware with a publisher and subscriber, and it's practically exactly the same.
Okay. Is it managed? Because the main pain point around Kafka is actually managing it, because you usually need a dedicated team of ops, just to, 4 to 5 people, just to actually manage that at Apache Kafka, especially if you have a big cluster with 10 or 20 brokers. But, yeah.
Although you can use a managed Kafka service in AWS, for example.
Yes, you can use a managed service. And actually, that's my recommendation. If you want to progress fast, you just go for the managed service. There are plenty of cloud providers that offer Kafka as a managed service. So you have Azure, AWS, Google. Also, I think they offer. But you also have Confluent, which is the main provider for Apache Kafka.
Sorry, time's up. We can upload again.